Hi everyone, welcome to another session of XUBS Explore the Depths. In previous classes of this series, we discussed about the fundamentals of electricity and the basics of power generation techniques and also the different types of power plant methods. In today's short video, we're going to discuss the basic concepts behind voltage and current. You will be handicapped if you don't know the basic principles behind voltage and current. As we are approaching the deeper subjects in electronics domain, it is mandatory that one knows about voltage and current concepts. This short video is not gonna make you an expert of these subjects, but the intention is to give you an introduction about the very fundamental ideologies behind voltage and current. Let's begin with voltage. Before we talk about voltage, let's understand what is potential energy. In physics, potential energy is an energy held by an object because of either its position relative to other object or stresses within itself because of its electric charge or any other factor. An energy held by an object itself. It need not be transferring any energy, instead it is potentially capable to deliver an energy. Let's look at a picture here. This setup has got an elastic potential energy, but this is not delivering any energy, but it is potentially able to throw this white object to this bottle when this elastic is released, right? So this is where we call this as this has got potential energy. That means it is potentially capable of delivering some energy when it's needed. This is a very famous water analogy in electronics to explain what is voltage and current. This setup has got a water tank which is several feet away from the ground, that's its height from ground, and the water is stored through this pump in the water tank. So there is water is filled in this water tank. This setup has got certain potential energy acquired by the storage of this water, because if I have outlet from this water tank, this gonna throw the water, this gonna let the water to flow this from this tank to the ground. So this energy is potentially capable, or it's a potential energy that is capable to deliver some energy when it is needed. Now, how could I relate this to the voltage in electronics? For that, let us try to analyze this in one more step deeper. If I increase the height of this tank from the ground level, then the water force or the power of water flow that I'm gonna see through this tank and the pipe is gonna be higher, right? So in equations I could write in this way that the height of the water tank or the power of water flow is directly proportional to the height of water tank. Similarly, voltage is also something that as the voltage increases, then total power delivery increases. What makes the power to deliver is the flow of electrons, and voltage is the one that pushes the electrons. The height of the tank pushes the water flow. Similarly, the voltage is the one that pushes electron to flow, and higher the number of electron flows, power is high. You could relate power of anything, power of a TV, power of a fan, power of a motor, power of any equipment. So the power is increased, that means the flow of electrons is increased, pushed by voltage. Very similar to what the push that happened by the height of this water tank. Let's look at another picture here in which the voltage and current is denoted. The potential energy that is acquired by the storage of this water is very similar to the voltage concept, because the height of this water tank or the water storage increases, power for the water flow also increases, or the push for the water flow increases. Similarly, in an electronic setup, the voltage increases, then the push for the electron to flow also increases. For us to understand now, I would call voltage as push for electron to flow, and electron flow is that everything that matters to us in the end. Let's take a look at another picture. As I briefed before, as the height of the water tank increases, water flow power also increases. The force of water flow also increases. Similarly, as the voltage increases, the push for electrons also increases. Very similar to what the setup shows you. The potential energy valid when this is several heights away from the ground. I could denote these points as A sits, and the point B is ground. Then I could mention this as a potential energy between points A and B. And it is also very clear that the potential energy will be always between two different points. Similarly, voltage is also is gonna happen if there is different points, or it's basically any voltage you could mention between 2 points. The voltage exists only if there is a difference in 2 points. Otherwise, it's 0 volt. If the water tank is grounded here, then there is no potential energy. If 2 points in an electronic circuit is been shorted, it's a single point. That means the voltage is 0. So let's look at finally the definition of voltage. That's as we just explained. Voltage is the difference in electrical potential energy per unit of charge between 2 points. So it's basically there has to be difference between 2 points, and voltage is nothing but the difference in electrical energy between 2 points per unit of charge. A diagram here which is more closer to the practical circuit. All of you are familiar with the batteries. I have taken a 1.5 volt battery here, and assume that there is a man inside this battery. I would call his capacity is 1.5 unit, because this man is gonna push the electrons inside this, and when the circuit is closed, the electron is gonna flow. If I have a battery which is 15 volt, I would say man inside this battery. It's just an assumption. So a man inside the battery who pushes the electron is much stronger. He has got much more better muscles. That means he could push with 15 unit force. So higher the voltage, the capability to push electrons is higher. Now, how would I relate these to the practical circuits? In our wall plug in our home, you're gonna see 230 as the voltage. In certain countries like US, it's 110 volt. So it's basically, as I said again, the voltage increases, the power of push increases, and also the difference is that in wall plugs, what you have is AC voltages. That means a push for one cycle is in one direction, from plus is here and negative is here, and then in the another half cycle it is the other way. In the batteries, always you're gonna have a plus at one end and the negative at another end. Just like call this as DC. In this case it was AC, and this is DC. AC is alternating current because its voltage push changes its direction in specific intervals. In DC, it's always one direction. We'll talk about the concepts of AC and DC in very detailed way in the coming classes, but this was just to give you a brief about what it means. Now, in practical cases, just to give you an example, you're gonna have this wall plug at your home, and you're gonna connect a mobile charger to this wall plug, right? Where the mobile charger is gonna take a cable and it ultimately connected to your phone. This 230 volt is when this is connected to the battery charger or an adapter. These two pins of the adapter is also going to see 230 volt, and there is a circuit inside this adapter which converts this 230 volt to 5 volt, because if you give 230 volt directly to the mobile phone, it's gonna blast, because it could withstand only to 5 volt. The reason why I explained this scenario is this is something that all of you are very familiar with. This example tells us that all the equipment that you use has got a voltage rating, whether it is a TV, whether it's a radio, all of that has got a voltage capacity. For mobile phones, it is 5 volt. You can't give more than that. There are a lot of new technology that accepts even slightly higher voltages, but typically you could consider it as 5 volt. TVs, you can connect 230 volt directly because there are internal circuits that converts this voltage to different voltages. Some of our smaller LED lights that stands like this, red and green and yellow and all that, this has got much lower voltage level, such as a certain 0.5 volt to 2 volt. all the equipments has got a voltage rating that says that if you apply a voltage larger, very large compared to what it expects, then the device is gonna blast. Now when we get deeper to the board level designs, you would see that in every tracks, every wire, every point, we are going to measure the voltage with respect to the reference point, and the voltage is going to give us a lot of idea about what happens inside the circuit. In all these examples I spoke about was voltage acting as a power source, right? Something that delivers electrons and power for the device to be operational. But voltages are also very well used as signals in communication world, in sensing worlds and all that. For example, if I want to send a message to you, then my electronic equipment might generate a signal like this. Of course it's not accurate, but might generate some certain signal like this. So if I measure the voltage levels, it's basically 0 and 3.3 volt, or it may be sometime 5 volt or any other voltage level. But basically what I wanted to say is that the voltage levels can not only be used for power transfer, but the voltage level, the change in voltage level, can also be carrying an information. It is also could be carrying a signal. So there are a lot of things happens when we get in deeper. Let's wrap up our voltage discussion over here and then move on to the current. Moving on to the current, let us recall the same water tank analogy here. So we very well familiar with what is voltage. That's nothing but the difference between 2 points, and the height of this water tank is what very similar to the voltage in our example here, and that's what gives extra push for the water to flow. In case of current, that's nothing but the quantity of water that flows through the pipe. To give another perspective, the impact of the water flow, if I measure the power or the impact that is created by this water flow or by this setup, then I'm gonna see a larger impact if the quantity of the water flow is high, and also when the height of the water flow is high, right? So the quantity of the water is what we related to current, and the height of the water tank is what we related to voltage. And the impact or the impression, the force of the waterfall is a combination, or it is affected by both voltage and current. In engineering subjects, we denote voltage by letter V and current by letter I. Now let's look at another example. Assume that I have a 1-inch pipe here which delivers a current of certain amps. Ampere is the unit of current. We shorten and call it as amps. So assume that 1-inch pipes allows a certain amount of water to flow that is equivalent to 1 ampere of current. Now if I have a larger thickness of pipe, let's say there is 3-inch pipe, then I'm gonna have 3 amps of current to flow, a water that is equivalent to 3 amps. Now relate these pipes as a wires or tracks in the circuit boards. The amount of current that flows through certain tracks and wires can be very much related to the quantity of water that flows through. Let's see what are the impacts if the quantity of water flows, that is very similar to the quantity of current increases. Just trying to get 2 examples interrelated. So if the current is higher, that means the total power impact that I'm gonna see where the water falls, right, is gonna be higher, right, because my current is higher. Second, I need to have stronger pipes over here, right, because now the amount of water is high. So what is that in electronics? What is that carries current? That is either tracks in a PCB board or it's wires. That means we need to have stronger wires when the current is higher. And the third point or third impact is that as the thickness increases, then the current flow also increases. Or when the current is high, that means the thickness is high, right? We just explained about certain aspects of current. Let's move on and try to dig in more detail in this. In our very first video, when we explained about electricity, we also explained about the atomic model, and we understood how the electron flow happens and what are the conditions for the electron to flow. So basically we know that current is nothing but flow of electrons. We want to relate that to the practical world. We know that ampere is the unit of current. But how much electron flows when we say there is 1 amps of current flow? Let's look at the details. This is a diagram of a conductor, or we can assume it as a wire where the electrons is flowing. When I say 1 ampere of current is flowing through this particular wire, that means there are 6.24 multiplied by 10 raised to 18 electrons flowing through this wire in a second. 6.24 multiplied by 10 raised to 18 electrons flowing through certain point per second is when we call this as got 1 amps. If it is 2 amps, just double of it. It is not important to remember this figure, but this was just to give you an idea about how much electron flow happens in a conductor when 1 amps flows. Little more closer to the practical world, I have a battery here and I have a copper wire through a bulb. Now the bulb will glow when my battery is connected to through a wire. So assume that I have a 3.3 volt battery here. That's my voltage, and if the bulb is consuming 1 amps, that's my current, or I would start denoting it as I now. If I break this path, assume that I just broke this path now, that means the voltage will be still seen here, right? If you recall, that's what we explained about potential energy. It's an energy held in an object and which is capable of delivering in practical energy when it is needed. The voltage will be still seen here, the voltage 3.3 will be still seen, but the current will be zero, because current always needs a closed path to conduct, closed path for the electron to flow. Otherwise there will not be any current. If I close this circuit once again, if I just short it again, then I'm gonna see 1 ampere of current to flow again. And the flow of electron always happens from negative to positive, and we call current flow from positive to negative, right? So electron flows from this side, then we assume current to flow to this side. It is actually an engineering mistake that was happened during the time of invention of all these technologies and the theories. Scientists assumed that the current is flowing from positive to negative, and all the calculations and inventions and the base materials and all that was prepared based on that, and we are following the same mistakes. But it is convenient, it is it is just a directional change. We don't have any issues in current that flows opposite to the electron flow, right? But in practically, if you look at in a molecular level, electron flow actually happens from negative to positive, right? But for the EC of engineering, we always assumes current flows from positive to negative. To give you an idea about the current consumption by certain practical devices which you are familiar with, the antenna of your mobile phone consumes only about 1 nanoamps to 1 microamps, hardly any current, right? But still there has to be a current flow to keep that alive. A TV remote consumes 10 milliamps. 50 milliamps is the consumption of your keyboard and mouse. Even some of the latest technology has got even lesser than that. A high power flashlight like an LED light or a flashlight is consuming 1 amps. A typically laptop powers are around, or the current levels is around 3 amps to 4 amps. And the motors that runs for your vacuum cleaners and also microwave ovens and such high power equipments consumes about 15 amps. A bolt of lightning, that's a thunderstorm and lightning, that's about kiloamps, right? Tens of kiloamps. Now none of this gives you an idea about what is the power consumption, but it only gives you an idea about what is the current consumption. And power is nothing but voltage multiplied by current. So you need to know both voltage as well as current in order to calculate what is the power. And time to give a definition to current. As we explained so far, it is simple. It is nothing but the number of electrons passing a given point in 1 second. So now when you see that a wire that is used for certain operations, you should be able to assume that there is certain amount of electron that runs so diligently with all its energy from one point to another point to make your equipment working. Having said that, time to wrap up. For that, quick practical examples. All of the equipments, and somewhere on this equipment, its voltage as well as current will be written. What's its voltage level and current level. If you are new to this subject, I would request you to take any of your equipment and try to look at what's the voltage and current levels of each equipment. It will give you an idea, and ensure that you are not applying any over voltage to any of this equipment. That brings to the end of our today's session. That brings us to the end of this today's session. I hope that you understood the basic principles behind voltage and current. In our next video, we're going to discuss about Ohm's law and the concept of resistance and how the power is calculated, and we're going to apply all these theories to certain practical circuits and see how these fundamental ideas could help us to solve some circuits. If you have any questions and comments and feedbacks, please let me know that in the comment box. Thank you for watching. Have a good day.